Hello everyone, and welcome back to the channel. Today, after much long-awaited time, we are finally going to be getting back into our systems design interview questions, starting off, of course, with TinyURL and PasteBin. Now, I've just had the absolute pleasure of going 20 minutes into this video and then realizing that my microphone wasn't turned on, and now I'm on absolute tilt. So if any of you think that you're not looking forward to watching this probably hour-long video, just know that I'm looking forward to recording it and editing it a whole lot less. Anyways, let's go ahead and get started before I freak out. So today we're going to be talking about TinyURL and PasteBin. And so the gist of these two is pretty simple. Basically, we're going to be generating short links. So in the case of TinyURL, we might have something like google.com, and someone wants to make a short link for it called tinyurl.com/abc. Same goes for PasteBin. If instead of entering my text here, I was to write Jordan is sexy, which we all know to be the case, of course, our paste would be pointed to by that short link. So let's actually go through some formal problem requirements. So basically, what we're going to talk about today is a couple of important things. The first thing is generating this unique short URL. Now the unique short URL, more or less, has to be unique. Obviously, like I've just said, but this is easier said than done, and it's of course going to make our service slower. So the other thing is that in addition to that URL, I'm actually going to make this problem a little bit more complicated and hopefully a little bit more in depth by adding some amount of analytics. In this case, the number of clicks per link. Now you might think that this is super easy. As a matter of fact, it is not. And of course, the reason it's not easy is because we have to be able to ensure that this number is actually accurate. While it doesn't have to be there the second that click occurs, eventually we do need to know the right answer. So let's think about some performance considerations as well. Disclaimer, I doubt that if I were to build a real TinyURL site, there would be 1 trillion URLs that I have to support. Nonetheless, this systems design problem wouldn't be very much fun if there weren't. So, as a result, I'm going to name some obscene amount of scale, and then we're going to try and figure it all out. So let's imagine that for our median URL, we've got 10,000 clicks. The most popular URL is in the millions of them. So that's going to be quite a bit and make things tougher. Like I mentioned, there's going to be 1 trillion overall. And then if we're talking about PasteBin, certain pastes can actually be in the gigabytes, and others are going to be in kilobytes, probably the vast majority of those. So let's think that in that case, if we're just going to do some back of the envelope math over here, we've got 1 trillion short URLs times 1 kilobytes worth of pastes. That's going to be equal to a petabyte. And that is certainly more data than we can store on one individual system. We're going to have to be doing some partitioning at some point down the line. Another thing to note is just based on the actual use patterns of people who use TinyURL. A lot of people are going to be clicking the link a lot more than they are generating links. So as a result of that, we're going to have many more reads than writes, and that's probably the type of case that we want to be optimizing on. So let's go ahead and actually start by talking about link generation, because that is going to be the most critical part of this problem that we really need to understand. So it is possible, if we really wanted to basically just have some monotonically increasing sequence number for all of our short links, but I think that's a pretty bad idea because then you basically need to lock on that number every single time for every single request that everyone's making so you can actually generate that short number. Instead, what we should probably be doing is generating those links out evenly across our system, and the way that we can do this is using a hashing function. I think just to continue to make sure that we get very evenly distributed links, we should probably put in things like in the TinyURL case with the long URL, a user ID, and the create timestamp. So we've got one example of that over here. And as you can see, it's going to output some sort of string for us to use as our TinyURL key. And so the question we should now be asking ourselves is how many characters do we actually need in our hash result? Well, assuming that we're using 0 through 9 and A to Z, that gives us 10 plus 26 equals 36 possible choices per character. And so as a result, that means per slot we have here, we've got 36 times 36 times 36 times so on, which is 36 to the n combinations, where n is how many characters we're going to generate. And so as a result, if n is equal to 8, I looked this up on Google because I can't do this in my head, we have around 2 trillion combinations. And considering I said we need about 1 trillion links, that should be good for us. So the question now is, what do we actually want to do on hash collisions? Because when you only have 2 trillion buckets and 1 trillion things, you're probably going to have a decent amount of those. Well, in the case of a hash collision, at least on a single normal computer in our actual computer science programs, we basically have 2 options. One is that you can do something known as chaining, which is creating a linked list out of each hash key bucket. And the other is probing, which is saying, oh, if this bucket is already taken, why don't we try and put our value over here? Now, in a database, we can't really use a linked list, so probably the only feasible thing is going to be probing. So for example, if we had, the hash 32FC1CA8, imagine this was like base 36 or something, then the next hash to click is going to be 32FC1CA9, and so on. We can basically keep trying until we find an available one. Hopefully that makes sense. So now the first thing I wanted to talk about for this video is writing those URLs, actually assigning them, and then as a result, what type of replication that we need to use within our databases. So of course, even though we care more so about reads than writes, we are still doing a ton of writes. I mentioned there are going to be 1 trillion URLs. And as a result of that, we want to maximize that throughput. So the first question that I wanted to ask is, can we do so with replication? Can we use a multi-leader or leaderless replication schema? Because these are 2 ways of actually making sure you can speed up writes. It gives you the ability to write to many replicas, and as a result, you can increase your throughput. And the answer that I think is going to be the case here is no, sadly, you cannot. So let's come up with an example. Here's me on the right, Jordan, and here's a businessman on the left. We're both submitting URLs for generation to the database at the same time, and his is leading to mypresentation.com. Mine is leading to one of my favorite sites personally. And then at the same time, you'll notice that we've got the same short link. So as a result, we have a conflict. And so when it comes to things like multi-leader or leaderless replication, it's kind of arbitrary a lot of the time how you actually end up resolving which write is going to win. So let's imagine that we use last write wins, LWW, and my timestamp happens to be a little bit higher than his, mainly just out of random luck, because keep in mind we can't even trust distributed timestamps. So this server happens to have timestamp X, and this one's got timestamp X plus 1, so Jordan's write wins, and then all of a sudden this guy is reading Jordan's link. And he's saying WTF because he thought this was a business presentation. So in theory, if you wanted to play devil's advocate here, you could go and say that, well, okay, maybe a few seconds later, we could have told the businessman, hey, your write is no longer valid. But at least in my opinion, this is not going to be good here because most people generate their link, they copy paste it, they leave the site, and then they paste it elsewhere. So most of the time, I feel that you probably want to be giving them the right link the second they click that button. So of course, this is going to rule out all sorts of databases that actually use leaderless replication, and that's going to include any of the Dynamo style ones. So Cassandra, Scylla, Ryak, etc. We want to be using single leader replication. Okay, next we are going to be talking about caching, because caching is actually another way that you can speed up your writes, assuming you're doing it properly by using a write-back cache. And so, for example, we've got these 2 guys over here, which are basically in-memory databases. They're, Redis databases in particular. And the gist is that you can first write to them, and then eventually, some point down the line, you can flush those out. But what we encounter here is basically the same problem that we encountered above with multi-leader or leaderless replication, which is that no one really knows the second they make the write whether their link is valid or not. And as a result, if they send it around in the meantime, it could be someone else's link, and that would be a problem. So again, same issue as before. We can't really use write-back hashing to speed up our writes. That's unfortunate. What about partitioning? That's another way you can speed up your writes. The more partitions that you have, the more load you can put on each one, and you can spread things out a little bit. Well, in my opinion, this is a perfectly valid way of speeding up our writes, and we should totally be doing it. So we can actually just go ahead and take all of our short URLs and partition on those. So we've got all the ones from A through D over here, E through H on the next one, and so on and so on. And so you might notice that I'm actually partitioning by short URL range as opposed to hash range. My argument for that is that the short URL is itself already a hash, so things should be pretty evenly distributed. We shouldn't have to worry about load too much. Also, recall that I basically said whenever you want short URL X and you can't get it, you basically have to try X plus 1. And so as a result, X plus 1 would be on the same partition as X, so it means that you don't have to go to another partition randomly to make that right, and it should, in theory, increase latency. So Another thing that is important to know with partitioning in general is that we probably should be using some sort of consistent hashing. Reasoning being that with consistent hashing, as opposed to hashing where you basically do mod n, where n is the number of partitions with your short key, that basically it means that whenever the cluster size changes, fewer keys are going to have to be redistributed. So let's imagine this arrow right here represents everything on this node over here. And when I add a new node to the cluster, now the only thing that's going to be moving is this range over here, as well as just as opposed to just a variety of scattered keys throughout our hash range. And so that is going to help us quite a bit. Okay, so let's actually talk about our database schema and what things look like on a single node. So you can see I've got an index right here, or not an index, but an actual table, which has our TinyURL, and ideally we want this to be unique. Like I mentioned, we've got an actual URL, a user ID, a create time, an expire time. We'll talk about how to expire things towards the end of this video, and also a number of clicks, which again, we'll talk about towards the end of this video. So let's imagine we've got two users, user 1 and user 2. The way that we've organized our schema, we actually have a little bit of a problem, which is that in theory, they could be both adding the same row with the same key for their short URL at the same time, and our database wouldn't be able to do anything about it. Why? Well, normally you would want to be locking on this key. But in our case, this row didn't actually exist yet before they added them, and so we don't actually have anything to lock on. So how would a database internally actually go ahead and do something like this? Well, there's two possible solutions. One of which is called predicate locks. Predicate locks are pretty simple. They're basically just locks on rows that don't exist yet, and you specify a query on that row. So in this case, as you can see, we would be taking everything from the URLs table where the short URL key is the thing that the conflict was on. And so what this style looks like in turn is if user 1 says create the link, but also give me the lock on short URL X, user 2 can do the same thing. But the database is now going to come back and tell him to kick rocks because that is now taken. Then he's going to have to go back and create link x+1. And then finally the database can say OK. So a couple things to note here. First off is that predicate queries can potentially be expensive. Why? Because they have to go through the whole database and actually find all of the rows that potentially apply. So something that could make this a little bit faster is actually using an index on this short URL field. Why? Because an index basically means that this guy is going to be sorted internally. And as a result of sorting by TinyURL, now all of our queries are going to be O of log n on that field because we can binary search there instead of having to do a linear scan, which would be O of n. Additionally, note that right over here, we've got two sets of network calls made by the guy who basically lost the race condition and now has to try to get link x+1. What we could do instead is use some sort of stored procedure or advanced database function where it's like if x is taken, grab x+1 or something like that. And that way we could maybe do all of that writing with just one network call. Perhaps it would speed things up a little bit. Okay, another way that we could also handle this in addition to predicate locks is by actually materializing conflicts. So as opposed to locking on rows that don't exist yet, what if we actually just grab the lock on rows that do exist? Well, how can they exist? We basically just write every single possible key to the database. Now you may think to yourself, oh, this has got to be a ton of writes. We have 1 trillion possible short URLs, or actually 2 trillion because there are that many combinations. Well, keep in mind that basically there's 1 byte per character, there's 8 characters per short URL, and that actually only comes out to 16 terabytes, which is really not that much in the grand scheme of things. You'll probably still have to partition, but again, not that much data. And so now when user 1 and user 2 go ahead and try to both write to the same key, user 1 can go ahead and grab the lock, user 2 is going to lose, the database is going to say try again, and then he can try with a different row. Okay, now let's talk about potential database engines, because of course this is something we want to be thinking about as well. The first thing to note is that for a problem like this, we actually don't really ever need to do range queries, maybe with the exception of a predicate lock. So a hash index could be fast, but at the end of the day, we are storing about 1 petabyte of data, and your interviewer might not let you get away with that one. They might just say that's going to be too expensive. Choose an actual on-disk index to use. And so if we are limited to on-disk indexes, that gives us 2 choices. First off, the LSM tree. Second off, the B tree. Now the trade-offs for these are, in my opinion, somewhat simple. The LSM tree is going to be a little bit worse for reads because when you read, you typically have to read from multiple SS tables and possibly the LSM tree as well. And when you write, you're basically just writing over to the LSM tree, which is in memory. So that should be relatively quick. You'll flush it later. On the other hand, for a B tree, you're basically writing straight to disk, which is a little bit less efficient. But at the end of the day, when you're reading, you only have to traverse the tree one time. There's no concept of having to check multiple different files. And so a B tree is literally just going right through, finding the piece of data that you want, it's all sorted, and then you're good to go. So in this case, because we are prioritizing reads over writes generally here, I think I would like to opt for the B tree. Oops, accidentally did that, but I'm open to hearing what anyone else has to say there. So let's actually go ahead and choose a database because now we have some good parameters with which to filter our choices down. We've already said we want single leader replication. We've already planned on doing some amount of partitioning. We want a database that uses a B tree index. And personally for me, considering the simplicity of all of it, I think that would just make it MySQL for me. I could see why someone might say MongoDB if they're particularly inclined to NoSQL, but it's not like our data structures that we're using here in our data model are particularly complex. I don't really see the argument for a document data model, so I personally would lean towards MySQL. Okay, so let's start talking about read speeds, because that's the thing that we really want to be optimizing here. Like I mentioned, there are a ton more reads than there are writes. So far we've already discussed the fact that we're going to be using replication, not only for fault tolerance, but also to speed up reads. Because replication is going to allow us to read from our follower replicas in addition to our leader. And also multiple partitions, which also means that for every partition we're going to have less load as a result of the fact that there are now more places to actually read from, which is going to be really great. Now it is worth noting that in this case of single leader replication, because we are going to be using asynchronous consistency, or eventual consistency would probably be the better word to use, it is possible that a client over here could read from a follower, get some stale data where maybe it thinks there's no actual URL to redirect you to, when in reality there has been over here, but it just hasn't been replicated yet. I do think that in this case you could maybe add some application logic to go check the leader replica, but at the same time you should probably be careful with that. You never know how many times they're just like bots that are constantly spamming all of your followers to actually look for, redirects or anything like that. You might end up putting a lot of load on your leader as a result. Okay, so maximizing read speeds. We've spoken about replication, we've spoken about partitioning, but next let's speak about hot links, because I did mention that certain links are going to have a ton of traffic, they're going to have millions of clicks, and as a result we need to find a way to actually deal with those. It would be great if not every single one of those requests for a particular hot link result had to go to the database, especially because they're all returning the same thing. And so what would be a good thing to do here? Well, we should probably introduce some amount of caching. So again, the caching layer, the thing that's actually nice about it is, first of all, we can scale this thing independently. If we have, a ton of hot links, maybe we need more caches. Additionally, we can also partition the caches by the short URL in the same way that we would our databases, so that more or less all of the requests for a particular hot link can go to the same cache or same set of caches, and that way we don't have to basically recompute that value multiple different times on many caches. So as you can see, all these guys want ABC right here. The best thing to do is to all have those requests go to the top cache, and then maybe this guy would be, like H through Z requests or something like that. Okay, so we've already spoken about the fact that we want caching, but how are we actually going to make sure that the data that we want gets in the cache? Well, when talking about caching or CDNs or anything like that in general, there are two concepts that we have to consider. We can either push the data to the cache, basically in advance when it's created, or we can pull it in there. So in my opinion, I don't think pushing is really going to work here, because at the end of the day we don't know which links are going to be popular beforehand. There's no way on our servers to say like, ooh, I can tell this link is going to be super hot, let's put it in the cache beforehand so we can warm it up. No, that's probably not going to happen. So at the end of the day we're going to have to be pulling that data in there somehow. So there are basically three methods of writing data to our cache that we can consider. The first one we've already spoken about, which is the write back cache. We've already said we can't really do this because it's going to lead to data inconsistencies and write conflicts, which is not going to be feasible for us. The second one, which is a possibility, is going to be the write through cache. So in the write through cache, which you can see over here, the gist is basically that in addition to writing to the database at a given time, you also write to your cache. Now, if you need to, you can use two-phase to commit to make sure that they always stay in line, or you can just do best efforts, but the gist is you can do that. Personally, I don't think it's necessary for us because it's going to slow down our write speeds a lot, and the vast majority of these links we really don't even want in our cache in the first place, so it's not that useful to do a write through. In my opinion, we should probably just do a write around cache, which is basically where you just go and write to the database as per usual, and then as people will eventually read from the cache, the database will send its results first to the cache and then back to the user. So as you can see, that's what's happening down over here. And of course, we are obviously going to run out of room as our cache gets filled up with all of these short links. And of course, we want to keep the most popular results because that's how we get the most usage out of our cache. The way that I personally would do this is pretty standard, which is just least recently used eviction. Whatever entry in the cache has been least recently used whenever we're performing a read from it, get rid of that one, populate it with a new piece of data. Hopefully simple enough. Okay, so we've spoken about some reads, we've spoken about some writes. We seem to have a pretty fast solution in terms of our replication, our partitioning, our caching. But now let's actually go and talk about a potential solution for our analytics. So if you recall, when I showed us the database schema, we do have a column for clicks. And in theory, what we could do is just go ahead and update that, right? We've got, let's say, 100 for the short link ABC123. We could have the guy on the left increment it by 1 when he makes the click, a guy on the right increment it by 1 when he makes the click. However, what many of you might already be anticipating is that without any sort of locking, this is going to be a race condition. Why? Because this guy might read 100 first, this guy might read 100 first, and then they're both going to say set it to 100 plus 1, so now they're going to write 101, and this guy's going to write 101, and then this gets set to 101 instead of 102. And keep in mind that for very popular links, this is a real possibility. If you've got hundreds of thousands of people clicking it every single minute, you're going to have a lot of these conflicts, and you would need to implement locking. And when you're implementing either locking or atomic operations for something that's popular enough, the database might not be able to handle that. So keep that in mind. It's probably too slow using this sort of naive implementation. So what's a potentially better way that we can do this? Well, what if we were to use stream processing? So basically, my idea is that we dump the data somewhere where we don't need to grab a lock in order to dump it there, and then we can go ahead and aggregate it later. So in theory, we could dump it to a database, but the question is, do we need to dump this to a database? A database might be slower than just dumping it to something like a, in-memory message broker or a log-based message broker, because at the end of the day, that's basically just either something in memory or a write-ahead log that you're writing to. So again, I feel like we should rule out the database. It's just going to be slower to write to. And additionally, we've also got our in-memory message broker, which is good. However, I also did say that I want to ensure that the analytics results that we get are actually correct. Now, the issue with an in-memory message broker is that it's in memory, which means it's probably less fault tolerant, barring it using a write-ahead log. And as a result, even though it's super fast, it's not going to be as durable. And so what I would prefer to do is meet these things in the middle, use a log-based message broker, where everything is kept on disk. We've got offsets for every single entry, and essentially what we're doing is writing to a write-ahead log, and as a result of that, it is going to be durable. Now, an example of such a solution would be Kafka. If you want to use AWS, maybe AWS Kinesis, but let's try and keep things open source here, so I'm going to say Kafka. Okay, so now let's actually talk about the consumer of these events. How is it that once we have the events placed in some sort of queue, that we can go ahead and process them? What technology do we want to use to do so? Well, we've got a few options, one of which is that we could have something dump to HDFS or S3 or anything like that, and then eventually run a batch job on it. In my opinion, this would probably give us analytics too infrequently, but it really depends on your users, right? If they're content to have analytics once per day, then you could do that, but I feel like most people would like a little bit of a shorter granularity than that, maybe every couple minutes, maybe even every few seconds. So personally, I'm not a fan of the batch processing solution. Additionally, another thing that we could do is use something like Apache Flink, which is more of a real-time solution. So in this case, we would process every single event that we receive from Kafka individually. Now, personally, I don't also think this is necessary because at the end of the day, if we're processing every single event individually, this also means that every single event is going to lead to a write to the database, and there's not really any reason to put that much load on it. Now, to be fair, you could write custom Flink code that basically just goes and says, maybe every 10 that you'll upload to the database. But in my personal opinion, the best option here is probably just going to be something like Spark Streaming, where Spark Streaming natively supports something like mini batching, which is configurable, and we could just say something like, hey, give me mini batches of 100 clicks, and so as a result, every single 100 clicks, you would go ahead and write to the sink in that type of interval. So the very nice thing about these stream consumer frameworks, like Spark Streaming, like Flink, is that they actually ensure correctness, at least within the stream processing system. So they basically say that between every event that gets to Kafka and the actual eventual state of our stream consumer, that all of those events are only going to be processed once. However, spoiler, that is going to break down whenever you have some sort of external system like a database. So let's go ahead and talk about that. The question is, are our events actually going to be processed exactly once? If our thing here is just going to be, do plus 100, maybe not. Maybe things would be a little bit different if we actually aggregated the total count in our stream consumer and then occasionally updated the database, but I think it makes sense to basically just take every single mini batched event and then upload it right to the database. So again, like I said, my question is, do things actually get run exactly once, and is it possible to have certain race conditions that could cause us to have an incorrect click count? In my opinion, yes. So, like I mentioned, events are only processed exactly once internally. So that means within here, events are processed exactly once. But here's an example of something that can happen. From Spark Streaming, we say to the database, hey, add 100 clicks. And right before the database can respond, saying, hey, I acknowledge this, even though it went through on the database, for some reason this internet connection gets cut off, Spark Streaming goes down, and then when it comes back up, it doesn't see that database acknowledgement, it doesn't realize that the event was processed, and now it's going to have to process it again. So it's going to say plus 100 one more time, and that right there is going to be bad, because now we're going to have an incorrect count of clicks. So we've got a couple of options that we can actually do. The first is two-phase commit, right? We would have some coordinator node over here, which basically says, hey, are you ready? And are you ready to commit this thing? And assuming they both say yes, then it would say, okay, go ahead and commit it. Now that is notoriously slow. Ideally, we would like to avoid it. So maybe another better option would be to use something like an item potency key, where in addition to storing the total clicks count, let's say there are 1,500 clicks, the database also says, hey, the last key I saw was key number A1245Z. And so, let's say this first write was A1245Z. Whenever this next write comes along, because it is actually the same event from Spark Streaming, that would also have key A1245Z. And then the database would say, hey, wait a second, these two are equal, don't process this one, I don't want to listen to it. And that is one way of guaranteeing that our pushes to the database are in fact idempotent. Again, another way, like I mentioned, which in retrospect might be easier, is to just keep track of total count in Spark Streaming, because then we don't have to worry about external numbers being published. But that's also going to fail if we potentially have multiple Spark Streaming consumers. So again, I personally think an item potency key would make a lot of sense. The issue with the item potency key is, let's say we had 10 Spark Streaming consumers, SS, 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 and they're all publishing over here. Now we need to store this item potency key times 10 for every single publisher, which is inconvenient. If all of a sudden there are 100 publishers, now we need to store 100 extra keys. That's not great. How can we do this? Or rather, how can we get around this? Well, we could just make it so that we only have one publisher per row. So what I'm saying is that we would only have one instance of Spark Streaming per short URL. So let's say short URL ABC is only being published clicks by this guy right here. And so the way that we can do that is we can actually partition our Kafka queues and of course our Spark Streaming consumers by the short URL. And this way we ensure that basically only one consumer is going to be publishing clicks for a specific row at a time, which is really good. The first one I mentioned is that one, there's fewer item potency keys to store per row. And additionally, now let's say we had two Spark streaming things publishing to the database at the same time. They would have to grab locks on this row ABC because otherwise we would run into the same problem as before. We would have a race condition. And so again, we want to be trying to avoid grabbing locks whenever possible. Okay, hopefully that much at least has made sense. Let's quickly talk about expired links because this is definitely worth a discussion. So I mentioned in my data model that when you create the TinyURL link, you should have some field for being able to expire one. So let's actually just go ahead and use a batch job to do that. We probably don't need to run anything like Spark here. It's not that much data. I feel like a nightly batch job would do it. And additionally, you really don't even need a lock either because at the end of the day, you're only grabbing it for the row that's being read. So yeah, maybe you do need a lock for that particular row of the one currently being read, just so that no one is continuing to overwrite it while you clear out the data. But at the same time, the most expensive batch jobs are those that have to grab locks on everything because they're doing some sort of aggregation. And in this case, we're really not. I think a simple cron job would probably get it done. And the pseudocode that we would be running is right here, which is basically, if the time of the batch job is greater than the expired time of the row, just clear it out. And yeah, should be simple enough. Okay, let's finally talk about PasteBin, because so far we've been talking as if this was all TinyURL, and the reason I group PasteBin into this kind of video is because they're two very, very similar problems, but the one exception with PasteBin is that you can have super large pastes. And so like I mentioned, some of them could be in the multiple gigabytes of size. We are going to support that. And so as a result, we probably cannot be storing them as a field in our database. I did look it up. I think Postgres supports fields up to 4 gigabytes for long text, so let's imagine we could have one that's 10 gigabytes and it's not going to fit in there. So a few options that we have, one of which is storing them in HDFS, which we probably shouldn't do because it's generally more expensive, especially considering that we don't need the data locality of being able to run batch jobs where our pastes are stored because there's no batch jobs to actually run on them. We're literally just storing them and then returning them. So in my opinion, something like an object store like Amazon S3 would make a whole lot more sense. So, like I mentioned, likely preferable, cheaper, no batch jobs, blah, blah, blah. You just heard me say it. The other important thing to do is note that because these files are so large, we want to be able to deliver them to the user relatively quickly. And so some sort of caching would be of great use to us. Now, if you've watched my CDN video, you would know that those are great for things like static content, which our pastes are. You can't actually modify a paste after the fact that you've made it. And so again, a CDN is basically this geographically distributed cache, which is going to enable us to deliver those static files particularly quickly. We could again use some type of LRU policy to make sure that only the most popular pastes are going to be in there. And as a result, hopefully things should go well. So as you can see, what we would want to do, perhaps, at least in my opinion, is try and perform all of these writes in series. Because if we want all of these writes to go through 1, 2, and 3 to the CDN, to the S3, and to the database, then we would have to use some sort of two-phase commit, which again can get very expensive and annoying. So personally, what I would do is from the client, I would just first write to CDN. When that basically goes through, I would then write to S3. Assuming that still goes through, I would then write to the database. The reason I don't write to the database first and then S3 and then the CDN is that if the database write goes through and then the write to S3 fails, it's going to seem like a paste exists when the data for it actually doesn't. So it's more important that we get the data uploaded to our object store on our CDN first, and then after that we can go and talk about putting things in the database. So now you may note that I am actually writing to the CDN before pulling things in here. I think this is maybe one of the few cases where write through actually makes a lot of sense, because at the end of the day, if we use write around, we're going to have a cache miss, and that cache miss is going to be gigantically expensive for a 10 gigabyte file. So it would be greatly beneficial for us if that was already in the CDN, considering how few writes there are relative to reads. That being said, again, open to debate on this one. Whew, okay, take a deep breath, guys. We're almost done. So, of course, we finally made it to the last diagram where I've tried to put every single thing together. So let's go ahead and do that. Here's our writer. This is going to be someone who's generating a link. Here's our reader. This is someone who's going to be reading a link. So the writer is going to do the following. Assuming that this is for TinyURL and not PasteBin, then you're only going to be writing over to the servers. But if it is for PasteBin, like I mentioned, you'll probably be hitting S3 over here, and you're also probably going to be hitting your CDN, which will eventually geographically distribute that content as needed. So anyways, we've got a load balancer before we basically horizontally scale out all of our URL assigning servers. Note that I do have our URL assigning service as something completely different than our URL reading service over there on the right. However, I think in reality they would probably be on the same box. I mainly did it this way for clarity of diagram, though I do think it is fair enough to make them their own microservices, considering the fact that there are so many more reads than there are writes. So once we hit our assigning service, we're now going to have to hit a database and actually write our data. So as you can see, I have those partitioned by the range of the short URLs, A through L, M through Z. And of course, we've also got our single leader replication. Single leader rep. And this is going to be our URL table, which ideally should be stored in MySQL. Now, of course, like I mentioned, to be speeding up our reads, we also want some sort of distributed, partitioned, replicated cache, which we can just use Redis instances for. So as you can see, this is similarly partitioned by short URL, so that we can, deduplicate the amount of data that we're storing and just use the same caches for the same types of data. Now note that, for example, if there's a key that starts with A and it gets a ton of traffic, and there's a key that starts with B and it gets a ton of traffic, one cache might not be enough for that. So in those cases, we may have to actually get some replicas of a particular cache instance. Okay, so hopefully we've touched on that a little bit. Now let's start to touch upon reads. So we've got our reader over here, and the reader, in at least the TinyURL case, is going to go to the URL read. It's going to in turn return something from the cache, ideally, or if it's not in the cache, we're going to have a cache miss. That's going to go over to the database. The database is going to load the appropriate cache. And then as a result of going and clicking that link, we are going to now upload our click data, the fact that we performed a click, over to Kafka, which is over here. As you can see, again, we've got multiple different partitions to support the fact that we want just one Spark streaming instance publishing per row. And then we've got our Spark streaming layer over here, which ideally should be sharded in the same way that our Kafka queues are. Now, eventually, let's say every 10 seconds or something, or more so probably 10 messages, because this is mini batching, Spark streaming is going to say, oh shoot, I just saw, you now have 50 more clicks. Well, if there's 10 messages, you can probably only have 10 more clicks. And then it's going to go over to MySQL and do a single database upload, which is going to be a lot less expensive than having to grab a ton of locks. Now, of course, the last component of this whole system is, well, where are we keeping all of this partitioning info? How do we know what load balancer is pointing where, what database URL is what? That's what we have Zookeeper for, which is really connected to everything. Zookeeper is great. It is, completely consistent, and I should say strongly consistent, and it is a coordination service. It is effectively a nice key value store of all of the metadata information that we're going to need about the various pieces of our system. Whew. Well, guys, give yourselves a pat on the back. I certainly need one. I know this was a pretty long video. Hopefully the content was actually useful, because I now need to go cry a little bit. Anyways, have a great rest of the night. I will see you in the next one.